Welcome back, everybody. In this video, we're going to do a little introduction to inequalities. So I'm assuming that if I write down something like A less than or equal to B, this is something that is familiar to you. We are going to use a lot of different properties of inequality this semester, and I wanted to start with just a few very common ones that we just have to be able to use without thought. All right, so these are going to be some properties of inequalities. And this is certainly not a comprehensive list of all properties of inequalities. This is simply going to be a list of properties I know for sure we're going to be using a lot. So we're going to start here with three real numbers. Let's call them A, B, and C. And let's assume that we know A is no bigger than B. So such that A is less than or equal to B, right? So this is a nice way of translating A less than or equal to B. You can say A is no bigger than B. Okay, so we're going to write down three different statements. So the first statement is that if I add this number C to both sides of this inequality, the inequality is preserved. So if A is less than or equal to B, then I can add C to both sides and I still have an inequality. So A plus C is less than or equal to B plus C. And, well, when would they actually be equal? All right, because most of the time A, say, will be less than B. Could it be that A is less than B, but you add C to both sides and you get equality? And the answer is no. So with equality, if and only if A is equal to B. Okay, so if they start equal, then you add the same number, they'll still be equal. And if you add the same number and they're equal, then the original numbers must have been equal. All right, second statement. What if we know that C is not just any real number, but if C is non-negative? So if C is non-negative, then I can multiply both sides of this original inequality by C, and it will not change the direction of the inequality. So if C is non-negative, then A times C is less than or equal to B times C. Okay, and again, we want to know when could you have equality. And we almost can say the same thing with equality if and only if A equals B, but that's not the only possibility. All right, and I'm going to just pause here for a moment. Okay, try to see if you can think of another way that I could multiply by C and get an equality even though A and B were not the same to begin with. All right, did you figure it out? Okay, it's an extreme case, and it comes down to, well, why did I make this C non-negative instead of C positive? Well, it's because C could equal 0. And no matter what A and B are, if I multiply by 0, I'm going to get equality. So that's the other possibility there. So you have to be aware of that. Sometimes, I multiplied by C and I got AC is equal to BC. Oh, okay, so I guess A equaled B. Not if C was 0. All right, the third case, well, what if C isn't positive or 0? What if it's negative? So if C is a negative number and I multiply both sides of this inequality by C, well, multiplying by a negative number is going to reverse the inequality. So if C is negative, then A times C is now going to be greater than or equal to B times C. And because C is not going to be 0 here, I really can just copy this line here up through A equals B, and then I get a period, all right? I don't get the C equals 0 situation. Okay, so if C is a negative number, then the only way when you multiply AC that you're going to equal BC is if actually A and B were equal. Okay, so all of these are properties that you're going to want to spend some time trying to actually prove on your own. Probably the most important thing for doing that is saying, well, what was the definition up here? What did it mean that A was less than or equal to B? And really, this is just equivalent to saying that B minus A is greater than or equal to 0. Okay, so that's going to be important. And I guess you could say with equality, if and only if, if and only if A is equal to B. Okay, so you'd want to use this absolutely for sure if you want to try to prove these things. All right, now we've discussed the absolute value, and it turns out that in this course, the absolute value and inequalities are going to work really closely together, right? There's almost a symbiotic relationship. So let's write down another theorem. Okay, and this is going to talk about the absolute value and inequality. Okay, so in this one, I'm going to start with two arbitrary real numbers. So let's let A and B be real numbers. And let's take an epsilon. Okay, we're going to take a positive number epsilon. So we say, and let epsilon be greater than 0. Okay, the following statements are equivalent. Okay, meaning if you know any one of them, you know all the rest. Okay, so the first statement is if I look at the absolute value of A minus B, which get into the habit of thinking of this right now, right? The distance between A and B. So if the distance between A and B is less than epsilon, then this is going to be equivalent to, okay, here comes statement number 2. It's equivalent to saying that B is in the interval A minus epsilon, A plus epsilon, okay, which remember, this is the A coin of radius epsilon. Okay, so if A and B are within epsilon of each other, then B is in the A coin of radius epsilon. Of course, there's nothing particularly special here about B versus A. This is equivalent to saying that A is in the interval B minus epsilon, B plus epsilon, right? Which is the B coin of radius epsilon. Now note, this is not saying that the A coin and B coin of radius epsilon are the same. They're simply stating that the A coin of radius epsilon contains B, and the B coin of radius epsilon contains A. These are equivalent statements. And the fourth equivalent statement is that if I look at A minus B, that this distance is no bigger than epsilon, and it's at least as big as negative epsilon. And when I was in high school, I think this is how they actually taught us to interpret an absolute value written in this form, right? As if you had some difference less than some number, you broke it up as two inequalities. Okay, so that's especially if you're going to go teach high school, that's probably how they're going to want you to explain it. I'm not sure they really are interested in you talking about A coins of radius epsilon. But in any case, all of these, again, are going to come down to looking at your definitions. So if you want to prove these things, you have to say, what is the absolute value, right? And there's going to possibly be cases in some instances, okay? What I would absolutely recommend is that you draw some pictures. So for example, 2 and 3, it might help to say, okay, well, here is A and here is B, for example. Okay, it doesn't have to be that B is smaller, or B is larger rather, but I can draw a picture that way. Now I can put an A minus epsilon and an A plus epsilon, right? Well, okay, maybe I didn't make this far enough away because I want the B to be inside there, right? So if A and B are within epsilon of each other, then okay, maybe epsilon needs to be over here. So there could be A plus epsilon, and now maybe over here will be A minus epsilon. And so you can see B lies in the A coin. Okay, but if I also want to look at the B coin of radius epsilon, well, let's see. It looks like the B coin, I need a little room. Let's see, that could be B plus epsilon. And then we'll come over maybe about there. There's b minus epsilon. And you see again, a sits inside of the b coin. It's between b minus epsilon and b plus epsilon. Okay. Now this again is not a proof that this is true, but this is a graphical organizer. It's a way for you to see that it's true, and that might help you actually write down a proof. Okay. We're going to want some actual properties of the absolute value, particularly so that we can state one of the most important inequalities. So let me write down some. Now, this could have come in, two of these could have come right in the absolute value section, but we're going to put them all together in here. So just call these absolute value properties. All right, so I'm going to start with two numbers, a and b. So these are real numbers. Okay, and like I said, the first two of these do not depend on inequalities. Okay, so the first one, well, as a word or as a phrase, distance. Okay, remember the absolute value tells you the distance between two numbers. Distance is symmetric. Doesn't matter whether I ask you what's the distance between a and b or the distance between b and a. Those are the same thing. And written in terms of absolute values, this says that the absolute value of a minus b is the same as the absolute value of b minus a. All right. The second property is that the absolute value is multiplicative. Ooh, that's a big word. Okay, what does it mean to be multiplicative? It means that I have some sort of function, okay, and the absolute value is a function, and that if I multiply two numbers and then apply the function, that it's the same as if I apply the function to each number and then multiply. Okay, so let's write this out in symbols. If I take the absolute value of a product, then this is equal to the product of the absolute values. Okay, so that's what it means to be multiplicative. Well, if it's multiplicative, then maybe there should be something like additive, right? What if I put a plus instead of a times between everything? And it turns out that the absolute value does not work that way. So that's our third property. And this is the really important one, and this is where we need our inequalities. This is called the triangle inequality. And the triangle inequality says that if I add two numbers and take their absolute value, that this is not usually going to be equal, but it will always be no bigger than what happens if I take the absolute value individually and then add them up. So the absolute value of a sum is no bigger than the sum of the absolute values. Okay, well, could it ever actually be equal? And yeah, the answer is yes. So we can get equality, but only when a and b have the same sign. Okay, meaning they're both positive or they're both negative, or, well, they could both be 0. So they both have the same sign. Okay, so the interesting part of the triangle inequality is when you have something like a equals 5 and b equals negative 3, because then you really will have a less than, not an equality. Okay, so let's do an example here, because I'd like to see these in action. So let's say I have three numbers, a, b, and c. Okay. So let's start with looking at the distance between a and b. The distance between a and b, well, what I could do, just inside, I forget I have absolute values, and I just say, well, what if I put an a minus c plus c in here, right? Notice by doing that, minus c plus c is 0. I haven't changed anything. And then I have a minus b still. Okay, so I haven't changed anything, but I'm going to put some parentheses in here just to mess around. And now I have the absolute value of something. Okay, a minus c is just some number, plus some other number, c minus b. And the triangle inequality now says I can rewrite this as being less than or equal to the absolute value of a minus c, the first number, plus the absolute value of c minus b, the second number. And if I don't like having the c in the second position here, but the first position here, I could always rewrite this using property 1. Okay, so here was property 3, there was property 1. Okay, so I now have some inequality I've built up. It started with 2 numbers, a and b, and I ended up with a third number in there. Yeah. Okay, but there's other ways we could have manipulated this. Okay, let's try, here's an alternative way to manipulate. And this one, well, I won't even introduce a c. Okay, I'm just going to stay with a and b. So what if in here I did a minus, and now I'm just going to multiply a and b together. And you say, well, why'd you do that? Well, it doesn't matter why I did that. I can do it, all right? It's my math, okay? You can't stop me. Okay, so I'm going to subtract ab and I'm going to add ab. And then I have minus b again. So it's the same idea, right? Instead of a c, I just have a times b. I'll put some parentheses, finish my absolute value. Now I'll use the triangle inequality. All right, so there's number 3 in action. So this will be less than or equal to the absolute value of a minus ab plus the absolute value of ab minus b. Now, I notice I have an a in both of these terms here. So this I could factor out an a times 1 minus b. And over here I have a b in both terms, so I could factor that out. And I'd get a minus 1 times b. So, but I have this absolute value as multiplicative property, number 2, which means if I have the absolute value of a product, I can break it up as the product of the absolute values. So using number 2, I get the absolute value of a times the absolute value of 1 minus b plus the absolute value of a minus 1 times the absolute value of b. And again, if I want to swap things around because I know that the absolute value is symmetric, I can. So let me put the b first in this one. So I'm using number 1 now. And I have the absolute value of a times the absolute value of b minus 1 plus the absolute value of a minus 1 times the absolute value of b. And that's like not obvious, right? Like who thought that was going to be true when we started all this? Okay, so we're going to be using these kind of tricks, particularly this, hey, subtract something and add something, right? Which ultimately does nothing, right? We're going to be using that all semester long. It's a really handy tool in our toolbox. Okay, let's see. How about one more inequality? All right, so this one doesn't always show up, in the analysis textbooks as a tool that you're going to use a lot. But man, I'll tell you what, if you look out for it, you can use this in a lot of places. So we're going to do one more theorem, and this is called the AM-GM inequality. All right, so the AM stands for arithmetic mean, the GM stands for geometric mean. Okay, and I'll define those within the statement of this theorem. So let's say I have a bunch of real numbers. Okay, so let's call them A1 through, say, AN. And these are all going to be positive real numbers. Okay. So if I have positive real numbers, A1 through AN, then if I take the average of all of these numbers, okay, so I get that by adding up the numbers and dividing by n. Okay, and so you might remember this is called the arithmetic mean or average. I mean, you've probably seen it just as the mean, okay, but it turns out there's a lot of different types of means. And so we have to use an adjective to describe which one we're referring to. So this is the arithmetic mean, but this is what you learn in school, is the average. You add up your numbers, divide by n. Okay. There's another type of mean, though, and it's called the geometric mean. And that's where instead of adding the numbers, you multiply them together. So here I would take A1 times A2 times ... times A sub n. Okay, but it's not just enough to multiply them. We need to somehow mimic what we were doing over here. We add them, but then to get the average, right, we divided by n, right? So for multiplication, dividing by n isn't really the right thing to do. It actually turns out taking the nth root is the right thing to do. So I'll take the nth root of the product. Okay, and you can see now why I really want to take positive numbers is, well, if n is even and I start taking roots and I had some negative numbers in here, I mean, we could get into the imaginary world really, really quickly. Okay, and so this type of mean is called a geometric mean. Okay, and so that's where we're getting the AM and the GM from. Well, the only thing we're missing here is an equality. And so the equality here says that the arithmetic mean is always at least as big as the geometric mean. Well, we saw before, like whenever you have this greater than or equal to, you might know when are they equal. So with equality, if and only if all of these numbers, A1, A2, etc., are all equal to each other. Okay, so if you start with the same number, then the arithmetic mean, the geometric mean, they're going to be the same. In fact, they're just going to equal that one number itself. All right, so let's see an example, right? How do we use this? Okay, so kind of a clever problem here. So let's let x be any real number. Look, I'm not even saying a positive real number, right? Just have any real number. I want to prove that if I look at x squared plus 2 divided by the square root of x squared plus 1, that this is always at least 2. Okay, now you could go into Desmos and graph this, and yeah, you'd see it pretty quickly. Yeah, it looks like it's above 2. But how do we know? How do we prove this thing? Well, maybe we could use a little bit of calculus or something that might help us. But you know what? The AMGM inequality is going to be super fast. So first thing, let's take this x squared plus 2 and break it up as x squared plus 1 plus 1. Okay, and if I do that, then I notice here x squared plus 1 over root x squared plus 1. That's just going to be root x squared plus 1. And then I still have plus 1 over root x squared plus 1. Now, this root x squared plus 1, that is some positive number. All right, x squared plus 1 is definitely positive. Take the square root, that's always positive. So just for keep my cognitive load down, let me give a name to this expression. Let me just call this a. If I do that, then I have a plus 1 over a. Now, a, again, is a positive number. So I now have two positive numbers. I can use the AM-GM inequality on two positive things. All right? So AM-GM says if I add those together and divide by 2, well, I'm not dividing by 2, but I could always move this n to the other side of the inequality because n is positive. So this is going to be greater than or equal to 2, right? I'm moving the 2 on the bottom over to the other side. Then I take the square root of the product of these numbers, a times 1 over a. Oh, but a times 1 over a, that's just 1. And the square root of 1 is 1, and you multiply it by 2, and you get 2. And so look at that. The quantity we wanted to estimate, look at that. It's greater than or equal to 2. It's just right there. It was immediate, right? AM-GM inequality. All right, tell your friends. All right, that's enough for now. This is a long, long video, and but you're gonna have to spend a lot of time working on it. Get these properties down, and then in the future we might come back and work on some of the proofs. But you should try to do some of these on your own.